Hello, this is video number 29 on my single variable calculus 2. In this video, we're going to talk about arc length and area of polar regions. So first, we're going to talk about arc length of polar curves. Recall that arc length of a parametric curve x of t, y of t is evaluated by the integral of square root of dx dt squared plus dy dt squared dt. So now if we apply that to the situation of a polar curve given by r equals f of theta, and substitute that into x equals r cosine and then put it into this formula, we get a very nice formula. So let's do the calculation and then we're going to get to a formula that you'll have to remember. So we have dx dt d theta squared plus dy d theta squared. So let's take the derivative of these and then square them. So we have to evaluate this one. So what is derivative of x with respect to theta? Well, we'll have to use the product rule, so we get f of theta times negative sine of theta plus f prime of theta times cosine of theta, and then we will have to square that. So the first term gives us f of theta squared and then sine of theta squared plus f prime of theta squared and then cosine squared of theta. And then we have a 2ab from that term, and the 2ab is minus 2 f of theta, f prime of theta, sine of theta, and then cosine of theta. Let's do the same thing for derivative of y with respect to theta, and then we'll add them. So we get f of theta times cosine of theta, derivative of sine is cosine, plus f prime of theta times sine of theta, and then we'll have to square that. So if we square that, we get f of theta squared times cosine squared of theta plus f prime of theta squared times sine squared of theta. And now this time becomes plus f of theta, f prime of theta, sine of theta, cosine of theta. Now notice that these two terms cancel when we add these two. These two terms add up to 1. Sine squared plus cosine squared, that's 1 if we factor f of theta squared. These two terms also become 1, cosine squared plus sine squared. So we get this formula. We get that dx d theta squared plus dy d theta squared is f of theta squared plus f prime of theta squared. F of theta was r, so that's just r squared, and f prime is the derivative of r with respect to theta. So we get arc length is integral from alpha to beta, which are the limits of theta, square root of r squared plus dr d theta squared d theta. So let's do one example on this one. Find the length of the curve given by this. So if you recall, this is something that we drew in the previous video. This is a cardioid, so if you plug in 0, we get 2 for r, so it starts from here. Theta equals pi over 2 gives us r equals 1, and then theta equals pi gives us 0. So we get a curve like this, and the bottom is just the reflection of the same thing about the x-axis. So the arc length is going to be r squared plus dr d theta squared, and then we'll have to integrate that from 0 all the way to 2 pi. But because of symmetry, we can integrate from 0 to pi and then double that. So let's evaluate this one first. R squared is going to be 1 plus cosine squared of theta plus 2 cosine of theta. And then we'll have to differentiate r. So I'm going to move it here. Differentiate r and square that. Differentiating r, we get minus sine of theta, and then we are going to square that. So we get sine squared plus cosine squared here, which is 1, and we have another 1 here, so that gives us 2. So we get 2 plus 2 cosine of theta. So the arc length is going to be double integral from 0 to pi square root of 2 plus 2 cosine of theta d theta. If we factor 2, we get square root of 2 times 1 plus cosine of theta. Now we can use the double angle formula. So just to remind you, we had cosine squared of x equals 1 plus cosine of 2x over 2. So if we use this formula, we would get 2 integral from 0 to pi square root of 2. If we replace x by theta over 2, we would get 2 cosine squared of theta over 2 d theta. So what we did was we substituted x by theta over 2. So we get 1 plus cosine of theta all over 2, and then we solve for 1 plus cosine of theta. Now, inside the square root, we have a 4. Square root of that is 2. Multiplied by 2, we get 4. Integral from 0 to pi, square root of cosine squared of theta over 2 d theta. Now, theta over 2 is between 0 and pi over 2 because theta is between 0 and pi, which means cosine of that is in fact a positive number. So we can write this as 4 integral from 0 to pi cosine of theta over 2 d theta. Now we can integrate cosine. Integral of cosine is sine. So this is sine of theta over 2, and we have to divide that by 1/2. And then we have to evaluate that from 0 to pi. So if we differentiate sine of theta over 2, we get cosine of theta over 2 times 1/2. So when we integrate it, we have to divide by 1/2. So that gives us 8 sine of theta over 2 from 0 to pi. When we plug in pi, we get sine of pi over 2. And when we plug in 0, we get sine of 0. And this gives us 8. So the answer would be 8. Let's look at one more example on finding the length of curves. So this one is another curve that we drew last time. This is a spiral. If you look at the curve, it would start with theta equals 0. For theta equals 0, we get 3 as r. So you have 3 on this axis. And then it would spiral because as theta increases, it would go counterclockwise about the origin. And the distance to the origin rapidly gets larger. So it would look like something like this. So it would rapidly get larger. And this was up to 2 pi. So that's why I have to stop at 2 pi. Okay, so this is roughly what the curve is going to look like. So now we'll have to evaluate r squared plus dr d theta squared and then integrate that. So r squared is 9 e to the 4 theta, dr d theta is 6 e to the 2 theta, and then we'll have to square that. So that becomes 9 e to the 4 theta plus 36 e to the 4 theta. Adding these, we get 45 e to the 4 theta. So the arc length is going to be the integral from 0 to 2 pi square root of 45 e to the 4 theta d theta. So square root of 45 comes out and we get integral from 0 to 2 pi e to the 2 theta d theta. Square root of 45 is 3 root 5. Integral of e to the 2 theta is e to the 2 theta over 2, and then from 0 to 2 pi. And finally, we have to plug in the values. So 3 over 2 root 5 multiplied by e to the 4 pi minus e to the 0, which is 1. So that would be the answer to the problem. So the next thing we're going to talk about is area of polar regions. So let's start with a sector. So what's the area of a sector? So imagine you have a sector and the angle is theta and the radius is r. So area of this sector is obtained by looking at the area of a circle. So what is the area of a circle? The area of a circle is pi r squared. Now what portion of a circle is this? The portion is theta over 2 pi because a full circle has angle 2 pi and the sector has angle theta. So this is the area of this sector. Canceling pi, we get 1/2 theta r squared. Now let's imagine you have a polar region bounded by a function r equals f of theta and two rays from here. So this is alpha and this one is beta. The region we're looking at is this region. We're trying to find the area of this region. So what we do is we're going to divide this into pizza slices, into very thin slices. Each slice can be approximated by this formula that we found. So each area would be 1/2 delta theta and then radius. What is the radius? Radius is f of r, f of theta squared. As you let delta theta to go to 0 and the number of slices go to infinity, what we get is integral 1/2 f of theta squared d theta. So this would be the area of this polar region as you see in this formula. So we're going to look at a couple of examples on this one. Find the area of the region enclosed by the polar curve r equals sine of 3 theta. So the first thing we're going to do is we're going to draw this region. Let me just draw the curve r theta and then we'll put it on the xy plane. So when theta is 0, r is 0 as well. So when theta is pi over 6, r is 1, theta equals pi over 3, r is 0. Then the next one would be pi over 2. The next one would be 2 pi over 3. And then the next one, if we add, so 2 pi over 3 plus pi over 6 is going to be 5 pi over 6. And finally, we get 2 pi. Now, if we go beyond pi, we will get the same curve again, because if you add pi to theta, so theta plus pi gives us sine of 3 theta plus 3 pi, which is sine of 3 theta, but negative of that. So that gives us negative r. So if we look at r theta and negative r theta plus pi, these are the same points. So if we go beyond that, we're going to get the same point. So let's graph this one on the xy plane, and then we will find the area of the region. So on the xy plane, we'll start from this region, this piece. This piece starts with the origin, so theta and r are both 0. It goes all the way to theta equals pi over 6, so maybe like right here. So we get something like this, and the distance is in fact 1. Then it comes back down, so from top up there to the bottom, it comes back to the origin, and it goes from theta equals pi over 3 to theta equals pi over 6. So we get a curve like this. So this one is a rose, and this is one of the 3 petals. The reason we have 3 petals is that from here to here, we got this piece, and then we have 4 more pieces left, and those 4 give us another 2 of these. So let's draw maybe one more of these. So the next one is from pi over 3 to pi over 2, and it goes from the origin to 1, distance 1 to the origin. So it would be here if r were positive. We reflected about the origin, and that gives us this curve right here. And then we continue with this one, so we get this curve here. And then we have one more petal. So up to here, this is the curve. Now I'm going to use a different color. This piece here starts from 2 pi over 3. So 2 pi over 3 is here at the origin, and it goes all the way to 5 pi over 6. 5 pi over 6 is here, so we have something like that here, and then it goes back to the origin, and then again it goes back to the same curve as we discussed before. Now the question is, find the area of the region enclosed by this polar curve. So the area is going to be 3 times the area of one of these petals. So what's the area of one of these petals? It is 1/2 times function, which is sine of 3 theta squared d theta. So that was the formula that we found earlier. So now we'll have to find the limits of integration. They are from 0 to pi over 3 as we found earlier. And then the rest would be integration. So this is 3/2 integral from 0 to pi over 3. This one is sine squared. Sine squared is 1 minus cosine of 2, twice that angle over 2d theta. So this one is 3 over 4 theta minus sine of 6 theta over 6. So this is the integral, which is 3/4 times pi over 3 minus sine of 2 pi over 6 minus 0 plus sine of 0 over 6. So sine of 2 pi is 0. 0 is 0, sine of 0 is also 0. So when we multiply this out, we get pi over 4 as the answer to the problem. Before we get to the next example, notice that if you have a polar region bounded by two curves, so let's say the larger one, the one that is farther away from the origin, is r equals g of theta, and the one that is closer is r equals f of theta, and we are trying to find the area of here. So what we can do is we can find this area and then subtract this area from that. So we get 1/2 integral of g of theta squared minus integral of f of theta squared. So let's look at an example on this one. Find the area of the region that lies outside the cardioid 1 plus cosine of theta. So let me draw that one. R equals 1 plus cosine of theta. So we have done this one a few times before. So this is our cardioid, and this point is 2. And inside this curve, so r equals 3 cosine of theta. This is a circle, and we have drawn that before, but let's draw it again. So what we do is we are going to write down x equals r cosine of theta and replace cosine of theta by x over r. We get r equals 3x over r, which gives us r squared equals 3x, which means x squared plus y squared is equal to 3x. So we can bring it to the same side. We get x squared minus 3x plus y squared equals 0. Complete this square, we get x minus 3/2 squared plus y squared equals 9/4. So this is a circle centered at the point 3/2, comma 0, and the radius is 3/2. So it's a circle like this, and we're asked to find the area of the region that lies outside of the cardioid and inside this circle. Let's mark the region. So this is the region that they're asking us to find the area. So what we do is we use the formula that we just found. So the area is 1/2 integral, but I need the limits of integration. So limits of integration are these intersection points. So what are the intersection points? Well, to find the intersection points, we need to solve the system. So we have r equals 1 plus cosine of theta and r equals 3 cosine of theta. So let's plug that in here. We get 3 cosine of theta equals 1 plus cosine of theta, which is to say 2 cosine of theta equals 1. So that gives us theta equals plus or minus pi over 3, but of course we have plus 2 pi k. That doesn't really matter. So this angle is minus pi over 3, and this angle is plus pi over 3. So we can find the area of the top part and double, or we can just find the area from negative pi over 3 to pi over 3. It doesn't really matter all that much. I'll just do the top part and then double that. So this is 1/2 the area from 0 to pi over 3, but then I have to double that. And then the formula for the circle was 3 cosine of theta. I'll have to square that minus 1 plus cosine of theta, and then I have to square that as well. So the formula for the area is 1/2 integral, and then I had two pieces, so I had to double that. Okay, so that gets rid of the 2 over 2 becomes 1. So now we'll have to integrate this. So how do we integrate this? First, we have to expand this one. So we get 9 cosine squared minus 1 minus cosine squared minus 2 cosine of theta d theta. These two give us 8 cosine squared. So that gives us integral from 0 to pi over 3. 8 cosine squared. Cosine squared is 1 plus cosine of 2 theta over 2 plus, or rather minus 1 minus 2 cosine of theta d theta. Let's go ahead and simplify. We get integral from 0 to pi over 3. So 8 over 2 is 4. So 4 plus 4 cosine of 2 theta minus 1 minus 2 cosine of theta d theta. These two give us 3. So we get 3 theta plus 4 cosine of 2 theta. That's 4 sine of 2 theta. But again, because of the chain rule, I have to divide by 2. And then minus 2 sine of theta. And then I have to evaluate from 0 to pi over 3. Let's plug in pi over 3. We get pi, 3 pi over 3, which is pi, plus 2 sine of 2 pi over 3 minus 2 sine of pi over 3, and then minus everything else becomes 0 because sine of 0 is 0 and 0 is just 0. Now here we get sine of 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. Sine of pi over 3 is also root 3 over 2. So those two cancel. So the answer becomes pi. So last problem. Find the area of the region that lies outside the circle and inside the polar curve disk. Okay, so let's find out what this polar curve is. So this is again very similar to what we did before. 4 cosine, that's x over r. So this gives us x squared plus y squared equals 4x, which is x minus 2 squared plus y squared equals 4 by completing this square. So it is outside the circle of radius 2 centered at the origin. So it is this circle centered at the origin with radius 2, and inside the circle of radius 2 centered at 2 comma 0. So it is this region that we are trying to evaluate. So we have to find the intersection points again. Again, because of symmetry, we can find the area of this piece and then double that. Let's find the intersection point first. Well, the first equation is r squared equals 4. So that gives us r equals 2. We can plug it into the second equation. We get 2 equals 4 cosine of theta. So cosine of theta is 1/2. So we actually get the same intersection. So theta equals pi over 3 is the intersection that we get. So we can get that the area is equal to twice 1/2 integral from 0 to pi over 3, the larger one squared. So that was 4 cosine of theta, that one squared. And then minus the smaller one, which is 2 squared. So this would be the integral from 0 to pi over 3. 16 cosine squared is 1 plus cosine of 2 theta over 2 minus 4 d theta. So we can first go ahead and simplify, and then we can integrate. So this would be the integral from 0 to pi over 3. 16 over 2 is 8, minus 4, that's 4, plus 8 cosine of 2 theta d theta. Integral of 4 is 4 theta. Integral of cosine is sine, and then because of the chain rule, I'll have to divide it by 2. That's from 0 to pi over 3. Let's plug in pi over 3. We get 4 pi over 3 plus 8 sine of 2 pi over 3 divided by 2, and then minus 4 times 0, sine of 0, all of that is 0. So this would be 4 pi over 3 plus 4 times sine of 2 pi over 3, which is root 3 over 2. So the answer is 4 pi over 3 plus 2 root 3. So now we're going to summarize what we have done in this video. To find the length of a polar curve r equals f of theta, when theta is between alpha and beta, we sketch the curve, we find the limits of theta from the sketch if they are not given, and then we use the formula to find the arc length. The formula is integral of square root of r squared plus dr d theta squared, d theta. To find the area of a polar region, first, you draw the region, and this is really important to draw the region, especially if you are planning on taking Calc 3. It is very, very important to work on these from now. Draw the region, use symmetries to simplify your work if there is any, and then identify the limits of theta, and then you use the formula a equals 1/2 integral of g theta squared minus f theta squared. And that brings me to the end of this video. I will see you in the next video.